Alright, in this section, we're going to be talking about polar coordinates, but we want to talk about areas and arc lengths in this new coordinate system. So we want to recall from trigonometry that the area of a sector of a circle is given by 1/2 times r squared times theta, where r is the radius and c, or theta, is the central angle. So that's like right here in this diagram. If we were to look at this sector of a circle, its area would be 1/2 the radius squared times theta. So now imagine we're trying to find the area of this figure in the center of the screen. Well, we want to divide this into what we're going to call polar rectangles. So imagine we have these little sectors of a circle like this where we have our theta and we have our little things, and imagine now if we were to cover that entire region in these little sectors of a circle, we could then use our area formula up here to set up a Riemann sum. So we get that the area of each of these polar rectangles, a sub I, is 1/2 f sub theta I star squared times delta theta. So if we take our sum and then take the limit as n goes to infinity, this will converge to these two integrals. So let's go ahead and take a look at our first example. So we want to find the area enclosed by one leaf of this for loop rows. So our rows is given by the equation r equals the cosine of 2 theta. So we need to find, well, when does the curve equal itself? And when we look at this rows, it's going to do something like this if we were to trace it. So this equation is going to have many solutions. So we want to know, well, when does our radius equal to 0? So we need to solve the following. 0 equals the cosine of 2 theta. So if we take the inverse cosine of both sides of this equation, we have the inverse cosine of 0 is equal to the inverse cosine of the cosine of 2 theta, and they reduce out, and that gives us, we'll leave it as the inverse cosine now. So we have the inverse cosine of 0, and then those two guys cancel out, equals 2 times theta. So the inverse cosine of 0 is going to be 1 plus the period, or sorry, not 1. The cosine of 0 is at pi over 2 plus 2 pi n for our period equals to 2 theta. But the cosine of this function is also equal to 0 at 3 pi over 2 plus 2 pi n is equal to 2 theta. So then, solving each of these equations for theta by dividing everything by 2, we end up with theta is equal to 3 pi over 4 plus pi n, and we get theta is equal to pi over 4 plus pi n. So it seems like we're going to be getting all of the odd multiples of pi over 4, because if we look at this list, we're going to get pi over 4, 5 pi over 4, 9 pi over 4, dot, 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 and going the other way, we're going to get negative 3 pi over 4, and so forth. Doing the same thing here, we're going to get 3 pi over 4, and then we add those together, we get 7 pi over 4, 11 pi over 4. Going the other way, negative pi over 4. So combining all of these together, it appears that these are going to be all of our solutions. So it seems like this rows is going to wrap around and have a whole bunch. But we only want to find the area of one of these leaves. So we need to find 2 different ones. So if we check, if we plug in pi over 4, we're going to get, if we started looking at our equation here, if we plug in theta equals 0, cosine of 0 is 1, so that means when theta equals 0, we get this point 1. So just to be explicit, that's our theta and that's our r. And then it's going to travel to our first 0, which is at pi over 4, moving in this direction to this point at pi over 4 and 0. So then to move backwards, we would actually see that this negative pi over 4 over here would be the other 0 for that. So then that means in order to find the area of that rose, that leaf of this polar rose, we're going to have to integrate from negative pi over 4 to positive pi over 4. So now we have our formula, which is the integral from alpha to beta of 1/2 r squared d theta. So our area, not in green, is going to be 1/2 the integral from negative pi over 4 to positive pi over 4, 1/2 r squared d theta. So our r is the cosine of 2 theta. So we have the cosine squared of 2 theta d theta. So the first thing we're going to take note of is that this is an even function. Cosine is even and squaring is even. So the composition of 2 even functions is also even. So using the evenness, we're going to have 1/2 times 2 times the integral from 0 to pi over 4 of the cosine squared of 2 theta d theta. And then these reduce out. And to integrate even powers of cosine, we're going to need to use the trigonometric identity that the cosine squared of x is equal to 1/2 times 1 plus the cosine of 2x. So in this case, our x is 2 theta. So after applying our identity, we're going to have the integral from 0 to pi over 4 of 1/2 times 1 plus the cosine of 4 theta d theta. Well, we can just pull our 1/2 out in front of our integral. So we have 1/2. The antiderivative of 1 is theta. Antiderivative of cosine is sine. So we're going to get sine 4 theta, but then either by a u substitution or using the chain rule backwards, we have to divide by 4. And that gives us our antiderivative, and we need to evaluate that from 0 to pi over 4. So we have 1/2 times, plugging in our pi over 4, plus the sine, pi over 4 times 4 just gives us the sine of pi over 4, minus 1/2, the lower limit, which is 0, plus the sine of 0 over 4. So sine of 0 is 0. Turns out the sine of pi is also 0, and 0 is obviously 0. So that leaves us with 1/2 times pi over 4. So the area of that one leaf of that polar rose is pi divided by 8. Alright, so now it's time for a U try. So go ahead and find the area enclosed by one loop of the three-leaved rose r equals sine 3 theta. So we start off doing the same thing we did in the previous example by setting sine 3 theta equal to 0. Taking the inverse sine of both sides, we get 3 theta equals the inverse sine of 0. And the inverse sine of 0 is equal to pi times n for any n in Z. And this comes from the fact that we have 0, pi, 2 pi, 3 pi, and so forth are all of the zeros. So we have 3 theta equals pi n divided by 3 divided by 3. So we get our angle theta is pi over 3 times n. And if we plug in n equals 0, sine of 0 is 0. So for n equals 0, we get pi over 3 times 0 equals 0. Not theta, but 0. And then if we plug in n equals 1, we get pi over 3 times 1, which is pi thirds. So our limits of integration are going to be from 0 to pi over 3. And we have the integral then from 0 to pi over 3 of 1/2 r squared theta. Well, our r is 3 sine theta, so we get r squared is sine squared 3 theta d theta. So then, once again, we're going to need to use a trig identity. And we have the identity for sine squared of x is similar to the one we used in the previous problem, but instead of adding, we are going to subtract the cosine of twice the angle. So putting this in gives us 1/2 and 1/2 is 1/4. The integral from 0 to pi over 3 of 1 minus the cosine of, we have to double our angle, so we have 3 theta gives us 6 theta d theta. So now we take our antiderivative, and we have 1/4 times antiderivative of 1 is still theta, and the antiderivative of cosine is sine, so we get the sine of 6 theta divided by 6, and that gives us, we evaluate from 0 to pi over 3, so we have pi over 4 times, or 1/4 times pi over 3 minus pi over 3, plugging it in for 6 theta. 6 times pi over 3 is 2 pi, so we get the sine of 2 pi over 6 minus our lower limit of integration. So we plug in 0 minus the sine of 6 times 0 is 0 all over 6, and that gives us a whole bunch of zeros once again. So all of these guys being 0, 0, and sine of 2 pi is 0 gives us pi over 4 times pi over 3 gives us pi over 12. So the area of one leaf of this polar rose is pi over 12. All right, so let's take a look at our next example. So example number 2 says find the area of the region that lies inside the circle r equals 3 sine theta and outside the cardioid r equals 1 plus sine theta. So what we need to find is this angle alpha and this angle I can draw a straight line. Apparently not. Let's try that again. This angle beta, where these two things intersect. So in other words, we need to know when does this equal this. So we need to solve 3 sine theta is equal to 1 plus sine theta. So minusing sine theta from both sides, we get 2 sine theta is equal to 1, divide by 2, divide by 2. We get the sine of theta is equal to 1/2. Taking the inverse sine of both sides gives theta equals the inverse sine of 1/2. So the inverse sine of 1/2 has solution pi over 6, and the other solution on the unit circle is at 5 pi over 6. And each of these would have other solutions in as well, but we're only interested in these two positive ones. So then now we need to find the area in between those two curves. So we're going to integrate from pi over 6 to 5 pi over 6. And similar to what we did in earlier sections, we are going to have our two distinct curves here. So this guy right here is going to be what we're going to call our upper or our outer curve. And we're going to have this guy right here, which is going to be our lower or our inner curve. And just like we did in the previous section, to find the area between two curves, where it's going to be the upper minus lower, or the outer minus the inner. So our cardioid is this guy over here, so 1 plus sine theta, and the circle is r equals 3 times sine theta. So we're going to end up with this being our outer and this being our inner. So we're going to have 1/2 times 3 sine theta squared minus our inner, which is going to be 1/2 times 1 plus sine theta squared d theta. So now we need to evaluate this integral. So we can split this up into two integrals and pull out some constants. So 3 squared is going to give us 9, and then times 1/2 is 9/2. So we get 9/2 times the integral from pi over 6 to 5 pi over 6 of sine squared theta d theta minus 1/2 times the integral from pi over 6 to 5 pi over 6 of 1 plus sine theta squared, which will distribute out to get 1 plus 2 sine theta plus sine squared theta d theta. And we now need to evaluate each of these integrals. So one thing we will notice is I have a sine squared theta here and a sine squared theta here. So if I wanted to combine these two things together, I have a 9/2 here, and this guy would have a 1/2 here. So 9/2 take away 1/2 would be 8/2, which would be 4 of those. The integral from pi over 6 to 5 pi over 6 of sine squared theta d theta minus 1/2 times the integral from 5 pi, or pi over 6 to 5 pi over 6. Of 1 plus 2 sine theta. Now on this guy, we need to use the trig identity 1/2 times 1 minus the cosine of 2 theta. So 1/2 times 4 gives us 2 times the integral from pi over 6 to 5 pi over 6 of 1 minus the cosine of 2 theta d theta minus 1/2 times the integral from pi over 6 to 5 pi over 6, 1 plus 2 sine theta. So now we can do each of these antiderivatives. So we have 2 times the antiderivative of 1 is theta. The antiderivative of cosine 2 theta is negative sine 2 theta over 2. And then minus 1/2, the antiderivative of 1 is going to be theta once again. And then the antiderivative of sine is going to be negative 2 times the cosine of theta. And then we're going to evaluate this from pi over 6 to 5 pi over 6. So now, putting all of that into our calculator. So if we put our y equals, we get 2 times x minus the sine of 2x over 2 minus 1/2 times x minus 2 cosine x. And then we go alpha trace, and we have y of 5 pi divided by 6 minus alpha trace y of pi divided by 6. press enter, and we get this number, which should look a little bit familiar. So, as our decimal approximation, we get this value, or the value of the integral being pi. So find all points of intersection of r equals cosine 2 theta and r equals to 1/2. So we have a picture or a graph that was drawn, which will help us visualize. So looking at this, how many different points of intersection am I going to have? 1, 2, 3, 4, 5, 6, 7, and 8. So based on this picture, I should find 8 points of intersection. All right, so let's go ahead and do this. So we set our two curves equal to each other. So we have cosine 2 theta is equal to 1/2. And we take the inverse cosine of both sides. So we get 2 theta is equal to the inverse cosine of 1/2. And the inverse cosine of 1/2 gives us two solutions. So we get 2 theta is equal to pi divided by 3 plus 2 pi n. And we get 2 theta is equal to 5 pi over 3 plus 2 pi n. So we finish solving for theta. We divide by 2, we divide by 2, we divide by 2, we divide by 2, we divide by 2. And we get theta is equal to pi over 6 plus pi n. And we get theta is equal to 5 pi over 6 plus pi n. Okay, so let's find or visualize a few of these multiples. So I'm not going to include the pi, but let's put these in here really quick. So we have 1 over 6 plus x. And for our other one, we're going to have 5 pi, or 5 pi over 6 plus pi x. So this, and if we make a table of values, this is going to show us our different multiples. So we start looking at our solutions, and we don't really care about any of the ones that are bigger than 2. So, because 2 pi is 1 time around the circle, and we get these values here, but we have a little bit of a problem. So, when we analyze this, so it gives us pi over 6 and 5 pi over 6, 7 pi over 6 and 11 pi over 6. So that's giving us only part of our solutions, and then they start repeating again. So we should have gotten 8 points of intersection. We only found 4. But the graph shows 8. So why did we miss some of these other points of intersection? Well, let's take a closer look at r equals the cosine of 2 theta. So first thing, we're going to go hit mode on our calculator and change our calculator into polar mode. And then if we go y equals, here's our r, and we want to put in r equals the cosine of 2 theta. And if we graph it, it's really, really small, so let's change our window. Let's make our x min and x max 1 and 1. And same thing with our y's. So -1, 1, and 0.1. And if we graph now, we get our polar rose that looks like the one that we have over here for the most part. So let's make our zoom a square though. So there we get our polar rose, but now let's look at a table and see what happens. So our polar rose starts out here at r equals 1 when theta is 0, but as theta increases from 0 to 2 pi, well, let's go ahead and go to our window again. So 0 to 2 pi, let's look at our table, and let's do our table in 0.25s. So we'll notice as theta increases, all of a sudden something interesting happens. R is positive, but here between 1 and 1.25 radians, we're at negative 0.41 and negative 0.8. We set this equation equal to positive 1/2, but we forgot that in polar coordinates, you can rotate to an angle and then go backwards. So we also need to solve cosine 2 theta is equal to negative 1/2. And so if we set up that equation where we have the cosine of 2 theta equals negative 1/2 and solve, this will give the 4 missing solutions. So we just need to be a little bit careful when we do this, because we have to remember that points in polar coordinates can have multiple representations, which is different than how we can get them in Cartesian coordinates. All right. So now it is your turn. Please go ahead and do this U try. So find the area inside of one leaf, but outside of the circle for r equals cosine 2 theta and r equals 1/2. So luckily, we just found these. So using this same graph that we had, we want the area inside of a leaf, but outside of the circle. So in our picture up here, what we're looking for is this area right here. So this is going to be our outer curve, and the circle is going to be our inner curve. So now we need to figure out our points of intersection. So we know from what we found right here that this one is pi over 6. And by symmetry, this one's going to have to be negative pi over 6. Or even by symmetry, we know that we can just double that same region. So let's start off with the integral from negative pi over 6 of 1/2 times r squared. And our outer curve is this, so cosine squared 2 theta minus 1/2 our inner curve squared, which is 1/4. I'll write it out explicitly, so 1/2 squared, which is 1/4 d theta. So once again, we have to use our identity to integrate our trigonometric function. So we have 1/2 times the integral from negative pi over 6 to pi over 6 of 1/2 times the cosine, 1 plus the cosine of 4 theta minus 1/4 d theta. So we have 1/2, and both of these are even functions, so we multiply by 2, so the integral from 0 to pi over 6, these guys on the outside cancel, and if we distribute this into our parentheses, we get 1/2 plus 1/2 cosine 4 theta minus 1/4 d theta. Collecting our like terms, a half take away a fourth is a fourth, so the integral from 0 to pi over 6 of 1/4 plus 1/2 the cosine of 4 theta d theta. Finally, finding our antiderivative, we have 1/4 theta. Antiderivative cosine is sine, so we're going to have the sine of 4 theta divided by 4, and 4 times 2 gives us 8. And we evaluate that from 0 to pi over 6. That gives us 1/4 times pi over 6 plus pi over 6 times 4 is going to be 2 pi over 3, so the sine of 2 pi over 3 divided by 8 minus, plug in 0, and we're just going to get zeros all around for this one, because the sine of 0 is also 0. So 0 and 0. So we get pi over 24 plus, and the sine of 2 pi over 3. So 2 pi over 3 is in the second quadrant, which means its reference angle is pi over 3. So that's going to be a 1, 2, square root of 3 triangle, but in quadrant 2, our x is negative. And that's not going to be important in this case because the sine is opposite over adjacent, so we're going to have roots 3 over 2 times 1/8, which gives us pi over 24 plus root 3 over 16. And we could get a common denominator if we so desired, but that's a perfectly good answer. Okay, so since we just did a U-try, I'm going to do this last one. And it says, find the length of the cardioid given by this. So we have our theorem that says arc length. If r is equal to f of theta, and if f prime is continuous, then the length of that curve is the integral from a to b of the square root of r squared plus dr d theta squared d theta. So in order to use this formula, we need to know dr d theta. So the derivative of 1 is 0, and the derivative of cosine is negative sine. So then we need to simplify the square root of r squared. So that's 1 plus cosine squared theta plus negative sine theta squared. So we FOIL that out and we get 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta. And by the Pythagorean identity, so we know that sine squared theta plus cosine squared theta is equal to 1. So that's going to be 1. So 1 plus 1 inside our radical gives us 2 plus 2 cosine theta for our radical. So now we want to find the arc length of this cardioid. So we need to integrate over one period, which is 0 to 2 pi, of the square root of 2 plus 2 cosine theta d theta. So factoring out our 2, we can write this as the square root of 2 times 1 plus the cosine of theta. So pulling our square root of 2 out in front, we have the integral from 0 to 2 pi of the square root of 1 plus cosine theta d theta. So we need to use this identity once again by solving. We have the cosine squared of x is equal to 1/2 times 1 plus the cosine of 2x. Well, we have something that kind of looks like this, so we multiply both sides of this equation by 2, and those two guys reduce out. And that gives 2 times the cosine squared of x is equal to 1 plus the cosine of 2x. And if I let x equal theta over 2, putting that into our identity, we get the cosine squared of theta over 2 is equal to 1 plus the cosine of 2 times theta over 2. The 2's are going to reduce out. So finally, after all of that, we get 1 plus the cosine of theta is the same as 2 cosine squared theta. Well, that is exactly this. So we replace it with what it's equal to. And we have square root of 2 times the integral from 0 to 2 pi of the square root of 2 times cosine squared theta d theta. So now we need to simplify this, so we can pull out the square root of 2, which gives us the square root of 2, and then we have times the integral from 0 to 2 pi of the square root of cosine squared theta d theta. So it's really, really tempting to say, well, the square root of cosine squared theta is just cosine theta. But cosine squared is always non-negative. So if you square something, it's always positive, and if you take the square root of a positive number, you get a positive number. So normally, if we thought about it, what we would have, let's go ahead and change our calculator back to function mode. We're trying to find the area underneath the curve, the square root of cosine squared of x. So if we do a graph of that, oh, my window's not quite what I want. Let's make our x min 0 and our x max 2 pi. And sure, we can do that. So we get something that looks like this, and that's what our cosine function is going to look like. But if we tried to compare that to the square root of cosine x squared, which would just be cosine x, we're going to notice it looks the same, but instead of getting negative area here, what are we supposed to be getting? Positive area. So we have to be a little bit careful and remember that this is equal to the absolute value of the cosine of theta. So we're going to get square root of 2 times the square root of 2 is 2 times the integral from 0 to 2 pi of the absolute value of cosine theta d theta. So technically we could break this up into 3 different integrals. So based on what we saw here, it's positive, so cosine is positive from 0 to pi over 2, so we can just integrate cosine theta, d theta, but then it's negative from pi over 2 to 3 pi over 2, so we would subtract that area to make it positive, and then it turns positive again from 3 pi over 2 to 2 pi of, this time, cosine theta d theta. So then, taking our antiderivatives again, so the antiderivative of cosine is sine for all of these, so we're going to have sine theta evaluated from 0 to pi over 2 minus sine theta evaluated from 3 pi over, or from pi over 2 to 3 pi over 2, plus sine theta evaluated from 3 pi over 2 to 2 pi. So that's going to give us 2 times the sine pi over 2 minus the sine of 0 minus the sine of 3 pi over 2 plus the sine of pi over 2. So we're adding the sine of pi over 2 because I have a minus sine theta, and then you got a minus the lower limit, so the minus minus makes it positive. And then we get plus the sine of 2 pi minus the sine of 3 pi over 2. So now the sine of 0 is 0, and the sine of 2 pi is 0. I have then a couple of like terms. So these guys are like terms right here. So sine of pi over 2 and sine of pi over 2. So I get 2 times the sine of pi over 2. And I have these two guys are like terms. And that's going to give me minus 2 the sine of 3 pi over 2. And the sine of pi over 2 is 1, so that's 2 times 2 minus 2, and the sine of 3 pi over 2 is negative 1. So we get 2 times 2 plus 2, which is 4, and 2 times 4 gives us 8. All right.